Hello class, welcome to Geometry Lesson 11.1, Three-Dimensional Figures and Cross-Sections. So our essential question of the day is, how are three-dimensional figures and polygons related? So we want to identify three-dimensional figures and their relationships with polygons to solve problems. So let's talk about the basics of 3D solids. So a polyhedron is a three-dimensional figure whose surfaces or faces are polygons. So remember that the vertices of the polygon, which is the base of the polyhedron, are the vertices of the polyhedron. Now the intersections of the faces are referred to as edges. So here's an example of a polyhedron. This is known as a triangular prism. The base here is a triangle. Now you notice that the vertices are the sharp edges here. So the vertices of the polygon are the vertices of the polyhedron. And the intersections between the faces are the edges. So you see here, so for example, this would be a face and this would be another face. So you got a triangular face and a rectangular face. And these two faces have an edge, and the edge between these two faces is what we call the edge. And so there are a bunch of faces, a bunch of vertices and edges in this particular polyhedron. So here are some non-examples: spheres, cylinders, and cones. These are not considered polyhedrons as their bases are not even polygons, and in the case of a sphere, it's not even doesn't even have a base per se. So these would be non-examples. So these would not be considered polyhedrons. Let's take a look at two types of polyhedrons: prisms and pyramids. Let's go ahead and take a look at the prism. A prism is a polyhedron with two congruent and parallel faces, which we call the bases. Now the faces other than the bases are called the lateral faces. An altitude of a prism is a segment that joins the bases at a 90-degree angle, which we call perpendicular. The length of the altitude is the height of the prism. So a right prism has lateral faces which are rectangles, and the lateral edge happens to be the altitude. An oblique prism has lateral faces that are not rectangular. So in fact, they tend to be more parallelograms and such, generally. So they're not full-on rectangles where they're 90-degree angles. They're something other. So here's an example. We have a right prism on the left and a oblique prism on the right. So notice that the bases for the prisms, in this case, this is a rectangle base as well as a rectangle base here. So there's two bases, and they're parallel. And the lateral faces are, the ones that surround it, which are the four faces that surround it. So those are the lateral faces. And in the case of the oblique prism, we have the bases are the same, right? They're parallel. However, notice that the lateral faces are parallelograms. This is a parallelogram. This is not a rectangle for the lateral face. So let's go ahead and talk about naming prisms. So we have here example of 5 different objects, and they all have names. If we were to name them, so the one on the left is it's a Rubik's Cube, right? So it's a cube known as a square prism. Notice that the base is a square, and we extrude it or we extend it to get a height and make it three-dimensional, and therefore it's a square prism or a cube. Now the one on the middle is actually a combination of two shapes, right? You can think of it as a house, but the top portion of the house is a triangular prism. Notice that the base is a triangle and it extends to make the prism. Now the rectangular prism is on the bottom. Notice that the base is a rectangle and you extrude it or you extend it in order to make it, give it 3 dimensions, right? Now the one on the right is it's a bar of gold, as you tend to picture it. But the base of this is a trapezoid. So notice that the base is a trapezoid and then you extend it to make it 3-dimensional. So this is a trapezoidal prism. And funnily enough, the one on the bottom left, these are just pencils, right? Colored pencils. And normally you would think of colored pencils as cylindrical in shape, but if you actually look carefully at them, they're actually more hexagonal in shape. You look at this, that's a hexagon, and you extend it and it becomes a hexagonal prism. Same thing with the honeycomb. These are hexagon shaped, and if you extend each of the holes of the honeycomb, it becomes a prism, a full-on prism. This is going into the honeycomb, of course. There are prisms inside. So these are 2 examples of hexagonal prisms. So now let's talk about pyramids. A pyramid is a polyhedron in which one face, which we call the base, is a polygon, and the other faces, which we call the lateral faces, are triangles with a common vertex called the vertex of the pyramid. And the altitude of the pyramid is the right angle segment, perpendicular segment from the vertex to the base. The length of the altitude is the height of the pyramid. So the slant height of a pyramid is different than the regular altitude or the height. The height is a 90-degree angle to the base. Now the slant height is not a 90-degree angle, and it's the height of the face, of the lateral face of the pyramid. So just like prisms, there are right pyramids and oblique. So the one on the left is a right pyramid, the one on the right is an oblique pyramid. Now the slant height would be this distance here for this face. You see that face there, this triangular face? Well, this diagonal distance is referred to as a slant height, which we'll call L for slant height, as opposed to the regular height of the pyramid, which is at a 90-degree angle to the base. Now the base of the pyramid is obviously here is a rectangular shape, and you see that the lateral faces are triangles that have a common vertex that they meet. Hence the pyramid. So let's talk about some examples of pyramids. So you notice that the pyramids, the pyramid in the left, you kind of picture that when you picture a pyramid in a historical sense, right? Like the pyramids of Egypt or pyramids in other places, right? So this is what you normally think of as a pyramid, and this is a square pyramid in that case, where the base happens to be, a square or rectangular shape, right? So a square shape, and then it just kind of peaks at the top, right? That's a square pyramid with a square base. Now the one on the middle is actually funny. It's a funny example of a Rubik's. It's not a Rubik's cube, right? It's a Rubik's pyramid, I guess you can say, but it's a triangular pyramid. The base is a triangle, and the lateral faces are also triangles, right? That have a common point. This is a triangular pyramid. Now the one on the right is actually supposed to be more of a pentagonal pyramid, where you have, this is a pentagon, 1, 2, 3, 4, 5. However, from this point of view, I wanted to give you an example of what it might look like to have a trapezoidal pyramid, right? Imagine that you can't see that backside, and that backside is actually really big. So this would be an example of, say, if you were to picture a trapezoidal pyramid, then that's how you would picture it, right? Trapezoid at the bottom. Even though it's not supposed to be a trapezoidal pyramid, it's a good example to show you how one would look like if you were to make it. So we'll call this a trapezoidal prism, or pyramid rather. Sorry, I said prism. It should be pyramid. And the one on the bottom left is actually hexagonal. You can definitely tell here. 1, 2, 3, 4, 5, and 6. Okay, so it's hexagonal. So it's a hexagonal pyramid. And then the one on the right, bottom right, is, if you look at it, if you look all the sides, we have 1, 2, 3, 4, 5, 6, 7, 8. So this is actually an example of an octagonal pyramid. Interestingly enough, in real life, you can see it. All right, so let's look at some of these examples. How many of each of the characteristics are there for the figures? So let's label the bases, lateral faces, and so on. So for the pyramid, the square pyramid on the left, we have only the one base for the pyramid, right? So the pyramid only consists of one base. Now the faces, how many lateral faces? Well, there's 1, 2, there's a triangle on the back, and a triangle on the back left. So there's 4 triangular faces. So those are lateral, for a total of 5 faces for this pyramid. Now the vertices are just the corner points, 1, 2, 3, and then there's one in the back, and then here, which is a total of 5 vertices. And the edges, so if we were to count the edges here, the boundaries between faces. So this is one edge, that's another edge, that's another edge. So 1, 2, 3, 4, 5. And then remember, we extend this out. There's 6, there's 7 here, there's 8 here for the back part of the triangle there. So we get 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. Let's see, let's count it again. Let's make sure we count it right. 1, 2, 3, 4, 5, 6, 7, and looks to be about 8. So 8 edges, if we count it correctly. Now let's look at the one on the right. We have a trapezoidal prism, right? So the bases, there are 2 bases, right? They're the 2 trapezoids that you see on either end. That's 2 bases. The lateral faces are the rectangular faces. So we got this, let's draw those out, or let's highlight those. 1, there's the one on the bottom, right? That's 2. There's the one on the roof, 3. There's one here, that's 4, and then the one in the back, that's 5. So the back is a trapezoid. So there's really just the 4 faces rather. 1, 2, 3, 1, 2, 3, 4. The roof, the floor, and the left and the right walls. So that's the lateral faces for a total of 6 faces here. And then the vertices are the corner points. So 1, 2, 3, 4, 5, 6, 7, and then 8 on the back. So 8 vertices. And edges, so it's kind of all the edges. So we got 1, 2, 3, 4 on the back, 5, 6, 7, 8 for the 2 trapezoids, and then 9, 10 for the bottom floor, 11, 12. So it looks to be about 12. All right. So there you go. So that we have this. Now notice that there's a pattern that evolves here, that if I add these, I get 10, and 8 plus 2 is 10. If I add these, that's 14. 12 plus 2 is 14. There's a pattern that evolves here, and this pattern is going to work for these types of shapes. Now, if I look at these ones, these are not polyhedrons, right? We have a sphere and a cylinder. So for a sphere, there are no bases, really, because it only sits at the top, right? It only stands at one point at any given point in time, is the sphere. So that's not really considered a base. So we're going to call that 0. The lateral faces, there are no lateral faces for the sphere. It's just a one face. So it's just one face, but no lateral faces. Vertices, there are no vertices to be seen. There are no edges to be seen here. And that's going to be it for the sphere. Very plain. It's just a one face that goes all the way around. Now for the cylinder, we have the 2 bases, right? 1, 2. We have the one lateral face, so that wraps around. That's 1. It's considered a lateral face. We can consider it to be such, and then that's a total of 3 faces. Now for the vertices, there are no vertices here to be seen. Now edges are a little bit tricky. I mean, you can consider this to be an edge, consider that to be an edge. If you did, then that would be considered to be 2 edges, 2 boundaries there, right? So we can if we were to consider that, we would say 2 edges all the way around. All right, so we'll consider that to be 2. Now, in any case, notice that the pattern here doesn't work. If I were to do these, I get 3, and then 2 plus 2, no, that's not gonna make 3. And 1 plus 0 is 1, and then if I add 2 to that, that's not gonna make 1. So notice that the pattern that I mentioned earlier doesn't work here because these are not polyhedrons. So remember that pattern from earlier? Well, that pattern is referred to as the Eulers formula. If I were to add the vertices and the faces together, then it would be equal to the edges plus 2. And that's what we did earlier. All right, so Juanita wants to make a polyhedron-shaped game piece for a board game. If she wants a game piece that has 20 faces and 30 edges, how many vertices does the piece have? So if we want to figure that out, we use Eulers Formula. The number of faces plus the vertices has to equal the edges plus 2. She has 20 faces, and she has 30 edges. So how many vertices does this game piece have? Well, this is going to be 32. So 20 plus what is 32? Well, it's going to be 12. 12 plus 20 is, or 20 plus 12 is 32. So she has 12 vertices. Now this game piece is referred to as an icosahedron. You don't really have to know that name, but just thought I'd give it away. It's called an icosahedron. It's a 20-sided piece, 20 faces. And these are some examples of icosahedrons, some dice that actually have that shape. And notice that the largest number that you get is 20 because it goes from 1 to 20 because 20 sides. So that's a 20-sided die, set of dice there. Now for part B, can a polyhedron-shaped piece exist that has 4 faces, 5 vertices, and 8 edges? So a 4-sided, die, I guess, or game piece. Well, can that exist? Well, let's see. We have 4 faces plus 5 vertices, F plus V. And that should be equal to the number of edges plus 2. Well, we have 8 edges. Well, 8 plus 2 is 10. And 4 plus 5 is 9. So this cannot exist because by Euler's formula, it fails it, right? So this is going to be no. It fails Euler's formula, so it cannot be a polyhedron that would exist with that characteristic. All right, so let's look at cross-sections. A cross-section is the intersection of 3D solid and a plane. So if I take this 3D solid, which was referred to as an octahedron, it's called an octahedron because it has 8 sides, right? 1, 2, 3, 4, and then 4 on the bottom. So octahedron. So basically it's 2 pyramids put together, essentially. That's really what it is, two pyramids. So yeah, so for this octahedron, if I were to slice it in the middle, right there, well, notice I slice it and I look at a square cross-section. So if I slice it for n, I'm going to get a square, right? It's going to be a square cross-section, assuming this is a square pyramid. So the cross-section is a square. Now for m, if I were to slice it, say, this way, well, notice I slice it in half, so it's going to look like that. Well, what does that shape look like? That shape looks like a rhombus, where this is not a right angle, this is not a right angle. None of these are right angles, but these are congruent and these are not. Or these are congruent, these are congruent. That's a rhombus. So we're going to get a rhomboidal kind of shape, so some kind of rhombus shape. So that's how you identify cross-sections. So for the shape of the cross-section for n is a square, for plane M is a rhombus. So these cross-sections are actually 2D shapes formed by the intersection of a 3D solid and a plane. So let's describe the cross-section of this shape. We have a pentagonal pyramid. If we slice it parallel to its base, so now the base of a pentagonal pyramid is it's a pentagon. So if I slice it parallel, well, guess what? I get another pentagon, a smaller pentagon, but still a pentagon. So if I slice it parallel, then it's going to be a pentagon. Now, if I slice it perpendicular, so if I slice it at a 90-degree angle, maybe like this, where that's a 90-degree angle there, then guess what? I'm going to get a triangle off of this. If I slice it perpendicular, I'm going to get a nice little triangular shape. So I get a triangle. All right, so let's look at some examples of cross-sections. So we have here a rectangular prism, and we'll show you how each of the cross-sections look like when I rotate it, when I slice it in various ways. So here I'm rotating it, and I'm rotating it, the plane, so you can look at it. We still get a bunch of rectangles. Rotated the other way, we get still a rectangular cross-section, but different dimensions. Then if I put it back to normal, and then I adjust the height, it's still going to be a rectangle throughout the entire length. So still rectangular cross-sections. Okay, so let's look at the next one, a triangular prism. We have a triangle, and then if I rotate this plane, I still get a triangle, but then it becomes a trapezoid there. Now it's trapezoidal, and then if I keep going, then I get a rectangular shape if I do perpendicular. I rotate it, still at a kind of perpendicular-ish, we got a rectangle, and I put it back to normal, and when I do that, I go back to the triangle. That's parallel slice. If I adjust that parallel slice, it's still going to be a triangle throughout. A rectangular pyramid, if I slice parallel to the base, it's a rectangle because it's a rectangular base. If I adjust it, then I still get a rectangular shape, and at some point it becomes more trapezoidal, and then I go to the perpendicular, it becomes a triangle, you can see there. Then I can rotate it. If I rotate it, now that's more trapezoidal depending on the location of the slice. Then if I rotate it, then I get, the triangular slice there. That's another perpendicular slice. If I put it back to normal and I adjust the height, then I get various slices that are rectangles. All right, let's do a triangular pyramid. So again, the slices are going to be triangles. If I adjust it, it's still going to be triangular. So there's another triangle there. Then it becomes more trapezoidal if I do it that way. And then if I rotate it, again, we got a triangular slice, perpendicular. I adjust the height and so on. So let's look at a cylinder. So circular, if I slice parallel, it's going to be a circle. If I slice at an angle, it's going to be an oval. You can call that an ellipse. And then if I slice it perpendicular, I get a rectangle. Notice that if I slice it perpendicular, rotating it that way, it's still going to be a rectangle. And then if I bring it back to normal, and I can adjust the height, it's still going to be a circle throughout the entire length. For a cone, we have slice it parallel to its base is a circle. Slicing it at various angles, we get an ellipse, oval shape. We get a parabola, interestingly enough, that's a parabola. And then completely perpendicular will be a triangle. If I rotate it, it's still going to be a triangle that sweeps the entire cone. And if I do the height, then it's just going to be various various circles of different radii. For a sphere, we know that if I slice it in half, it's going to be a circle. Think of it as the Earth. It would be the equator. If I slice it at various angles, still going to be, it's going to be spherical at the very top if I do it perpendicular. And let's go back to that. Completely vertical. That's going to be equivalent to the prime meridian on the Earth. Various latitude and longitude and so on. We get a bunch of circles. Now those circles in the middle are called great circles, right? So that's a great circle, the equator. If I adjust it at various heights, I get different circles, right? The one circle that is the largest in the middle is referred to as a great circle. The other ones are not. They're just smaller. There is the South Pole at the very bottom and North Pole at the top, for example. All right, so if I rotate a polygon to form a three-dimensional figure, there's a way to do this, right? If you take a polygon and you rotate it around an axis, which we call the axis of revolution, you can actually form a three-dimensional figure that's round. So if I did this, it would be called a solid revolution. And if I take this rectangle and rotate it around this axis, notice if I keep doing that, I get a cylinder. And that's referred to as a solid revolution. So if I rotate this triangle, notice I rotate around here, I get a conical shape, a cone. If I rotate this, as I mentioned earlier, I get a cylinder. If I rotate this triangle, I get, guess what? Another cone. It doesn't matter if it's a half triangle or not. So let's show you some more examples. If I got a circle, a semicircle, I rotate it, well, guess what? It's going to be a spherical shape. Each of these is going to be rotated to make that spherical shape. If I revolve this circle, which is off-center, around this axis, well, I'm going to get a donut shape, which we call a torus. I rotate it around, around, and around, and around, and I have a gap in the middle, and that makes a donut shape. And then lastly, if I do this, I rotate it like this, and rotate like that, rotate like that, well, guess what? I get a conical shape, a weird cone. It's called a truncated cone, where it doesn't have the tip, right? It's just truncated. So that's called a truncated cone. So I'll show you some examples. If I rotate this cylinder around, or this rectangle, I get a cylinder. Rotate that around a full 360. There's an example of that. If I rotate a triangle, like I said earlier, that half triangle, I can rotate that and get a conical shape. And then if I do a trapezoid, I get a truncated cone. I just wrap that around, I get my truncated cone, which is more like a volcano shape. And then if I do that, rotate that, I get a spherical shape. There you go. And then if I do this circle and I rotate it, I wrap it around here, I get a torus, as you can see. There you go. There's my torus. And that's it. That's going to do it for the video, guys. I hope you found this useful. I hope you found this informative. As usual, I'll see you in the next one.